All right, welcome to the December 2021 webinar. Today I'll be talking about analyzing time history, actually a time series, to look at droughts and actually characterize droughts that have occurred over a historic period. And what I'll do today is I'll walk through the process of building a simple model that will walk over a historic time series that I've obtained from an online database, and then I'll show you how I um, walk through that time series, capture information about the time series, and then generate statistics that tell us things about the droughts. So, for example, what is the average duration of a drought? What is the magnitude of the drought? These are the kinds of things that we might want to use when we're building a model that, for example, might do a forecast into the future and simulate droughts going forward. So we can analyze the historic time series, generate statistics that will then allow us to simulate future droughts based on the historic record. So one of the real strengths of GoldSim is being able to simulate future conditions that we haven't experienced yet, but do it in a smart way. And a good way to do that is to evaluate the historic trends. And I have seen, and I've also done this with models where you take a historic record and you just assume that that would be similar going forward in time, and just use the historic record as a surrogate for going forward. In fact, you could even sample it using multiple realizations. Many of you have probably done this. I've done it too. And that's one way to simulate future conditions, simply by sampling a historic time series. But even more powerful than that would be to build a model that could look at potential events that have not yet occurred, but are based on the reality of what we have seen in the past. And so that's really what I'm trying to gain with this particular application, which I'm currently working with a researcher at University of Utah who studies droughts, long-term droughts, looking at paleo, reconstructed paleo records obtained from tree ring data mostly. And so what you're looking at right now, what you should be looking at, if I've got the correct screen being displayed, you should see a chart here that shows comparison time history at the top. And what this is, what you see in blue here is the reconstructed paleo records of annual total precipitation. And it's based on a number of various sites, and that's why it's called reconstructed. And so what it shows you is a comparison to this green dashed line, which is the average over all of these years. And you can see on the bottom, on the on the x-axis, we've got nearly 800 years of records here, all the way back to what would that be? 700? No, sorry, about 13, 14, 1400. And so what we're seeing here is quite a long time series record. And so what I did is built a model that looks at this, the blue line essentially, and compares it to the mean, the green dashed line. And we find the periods of which we have drought, and quantifies these droughts. However, what we're looking at are long-term averages. So the actual annual record is jumping a lot more than this. It's going up and down across that green line many more times than what we see here. I just wanted to show you the general trend over time. But what you can do then, once you understand and quantify the droughts and these periods in which this blue line dips below this threshold, this average, once you quantify that, then it allows you, then now you have variables that you can use to build a model that could simulate future conditions with similar statistics, similar types of droughts. That's what we were aiming for. So if I run this model now, I have shown in red a completely independent, well, it's not completely independent, but we're not sampling a time series of historic record to generate this red line. We are doing a model. We've built a model that synthetically generates its own precipitation record over time, and will with the goal of having the same statistics or similar statistics as what we found in the historic record. And so what that allows us to do is to generate a wide range of possibilities by running many realizations. So what you can see here is if I flip through the realizations by clicking on the up here at the top of the chart, you see we're looking at realization number 1. So if I flip through, you see that the red line changes as we go along. And if I looked at the probabilities, then you can see there's this range shown here. This is after running 100 possibilities or 100 realizations. And so we're still not done with this work. So far, what we have accomplished with this model is mainly fine-tuning and generating the ability to characterize these droughts and quantify duration, magnitude, and count the number of occurrences of the droughts. And we're going to use those numbers to complete the model of the future precipitation generator. And how could we use this? Well, we already in our library, as you might be aware, we already have a few climate generator type models. One of them is called WGen, and it has average precipitation as one of the inputs, but it has no way to accommodate large multi-year swings in the precipitation. All it does is you just give it an average, right, and then it generates daily precipitation from that. However, you might want to look at multi-year droughts because that's a reality. And so with this type of model, then we can drive the average essentially up and down like what naturally happens, and then have that be used to generate daily climate information for your future model, with it being based on historic record like this one. So that's the goal. That's where we're headed. But what I want to show you in this webinar is in a little bit simpler type of model, how do we characterize these droughts? How do we go about this? There are multiple ways, and I'll show you one. So I'm starting from scratch. Here's a blank model, and I obviously don't have time to build every single element. So I'll be doing a lot of copy pasting here, and hopefully that will still provide you with a view of how this model can be assembled. The very first thing that I want to do is find the historic record that I'll be evaluating. So what I did is I just went online and I went to I actually went to a snow gauge. It's a SNOWTEL site monitored, managed by the NRCS. And this happens to be a snow gauge that is located near us here in Washington on Mount Rainier at a place called Paradise, the main entrance to the national park. And if you look at this data set, you'll see that it starts in 1980 and it runs all the way down through to current. When I first captured this is November 18th, 2021. Okay, so knowing that, then what I want to do is I want to run a simulation that covers that period of time. So I'll go up here to the simulation settings and set that up. I want to use a calendar time basis because, well, our data is calendar time. So that just makes sense to me. So I will go ahead and set this up. And I realize that I said 1980 is when this data set started, but if you evaluate the data set, you'll see there's some missing values early on. So I'm just going to avoid those, and I'll just go ahead and skip all the way over to 1985. And then I want to end this January 1, 2021. I realize the data set goes all the way through November, but it's not a full year. I want a full year, so I'll just go to January 1st, 2021. Also note that this is where I see a lot of people doing this. I've gone all the way to January 1st, the following year, and I've seen people go to December 31st, in this example, December 31st, 2020, but that's going to be 1 day short of a year. I know that's a technicality, but to have it run through a full year, you would need to go to midnight on January 1st of the following year. So there are some things that you might get stuck on by doing this. For example, the model will run all the way through to the next year, but it doesn't really count because it went to midnight. But you will see that date on your x-axis. You just have to keep in mind that it didn't actually run in 2021. It just ended at midnight of that period. But just keep in mind that if you said December 31st, that's actually a day short of the full year. So to get the full year, I run all the way to 2021. Okay, so enough about that. Then also on the Monte Carlo settings, I just want to run a single realization, and it doesn't matter if I say deterministic or probabilistic at this point in time, because I'm not doing any randomness in this model at this point, but it doesn't matter, just to keep it that way. Okay, so I've got everything set up with that, and now just to test the model, that's the next thing I want to do, just to make sure that I've got everything situated correctly with my time series. So I'll just go ahead and run the model and then show a time history. Looks good. And by the way, if you hold down the control key, then you can zoom in and see more detail. This is daily precipitation here. And what I want to do is I want to do a couple of things. I want to look at annual total precipitation, and then I want to look at statistics of the annual precipitation values. Okay, so how am I going to do this? The way that I came up with was to use a SubModel, because I may want to be looking at the daily precip for other parts of my model, but at the same time, I also want to know what are the annual totals. So there are a couple of ways to do this. A very easy way would be to simply get those annual totals in a spreadsheet. And then once you have them, then you're done, and you have them in your just copy and paste them into your model. However, I wanted to use a SubModel because what if I decide, I want to use a different time series, I want to change it, something like that, then the SubModel will allow you to essentially accommodate any changes to the time series that you might have without having to go back into Excel and recalculate all those annuals and bring that back in. So that's the difference. But if you're only going to do it one time, then I would say just do it in Excel and then copy and paste them in. No reason to go through all this effort of a SubModel. But because I need to keep this quite flexible going forward, I decided to use a SubModel. Okay, so now with the SubModel, we're going to need a couple of things. We want to make sure the SubModel evaluates the entire time series that we're looking at. So I want to make sure this SubModel runs for the correct duration. When you first add a SubModel, you get this message that says, do you want to import an existing model as a SubModel, which is a pretty cool feature, by the way. Let's say you work on another model somewhere, you want to load it as a SubModel in here, then you could say yes, and you could import an existing model and have it come in as a SubModel to GoldSim. Those of you that have not used a SubModel before, this is it's a quite advanced feature, because it's another model running inside your model. sometimes it's a little bit difficult just to wrap your mind around what's going on here. But just imagine that at any point in time, you can tell this other model to run inside of the main model. When I say main model, I'm talking about this main part that we're looking at out here. Let me close this. So this is the main model, and this is going to be the submodel, is what I'll be referring to. Okay, so I just went ahead and closed the properties of this because I want to add a couple more things in here. I'm going to just add a couple of expressions here that help us define the duration that we want to run this submodel for. And I'm just going to copy and paste those over here. Okay, so here are a couple of expressions. This is the start date of what I'm assuming for this data set and the end date. But it turns out that what I could do with these elements is I could just assign these elements to run properties of GoldSim. So, for example, this end date just happens to be the end date of the simulation, and we can get to that information simply instead of by doing this. We could, instead of hard coding a date, we could just get a run property that's called start time plus sim duration, like that, and that would give us that value. Okay, so that's something you could easily do. I'm going to use the start and the end date for my time series that I'm looking at to define the duration to run this model for. So I'm going to open up the properties of the submodel and go to the interface, and instead of adding an output from the main model, I will go ahead and click on a submodel run property that I want to define myself. And this is a way to tell the submodel how many realizations to run, or in our example, how long to run, what the duration of the simulation of the submodel will be. So I'll click here, and then it's the first option here is the simulation duration. That's the one we want. I want the simulation duration to be the data end date minus the data start date. So that's now defined from the outside, which is a nice way to control the submodel. So I don't have to do it. I don't have to do it manually. The other thing I want to make sure I do is I want to look at the time series here and make sure that the start date is aligned with the data set as well. Okay, so now my submodel is ready to run. And the next thing I want to do is import this time series into the submodel. And I do that through the interface as well. One thing about a time series to keep in mind is that there are two outputs of this time series. If I click on the output port, you'll see that I have the value that the time series outputs at every single point in time during the simulation. That's going to be one value during each update time. But you can also refer to the definition, and the definition is the entire time series set. And so that's what I want to load into the submodel. So I'll go back to the submodel interface, and I will add now the entire definition of the time series. Okay, so now the whole time series is coming in, and now it's time to go into the submodel and start evaluating the time series. But before we do that, we need to add the time series and link it to the time series definition. So an easy way to do that is to simply copy the time series that's out here and paste it inside of the submodel. Now keep in mind that I'm not going to end up with the same time series. That would be a bad design, because what if you change the time series on the outside? So I don't just want to duplicate here. I don't want to just copy and paste this. What I want to do is I want to link this time series to the outside time series. And to do that, you change the data source from locally defined data to linked. And when you do that, you see a new link tab appears here. And then we simply right-click, insert link, available properties, and now we can access the definition from the outside. So that's how you bring the time series in. It is not defined, the data is not defined inside of this submodel. Instead, the data is defined outside the submodel and imported into the submodel. Okay, with that being said, now we are ready to calculate the annual sum, the annual sums of precipitation. And the way I want to do that is using using an integrator. So the first thing, in fact, before I do the annuals, I just want to calculate the total precipitation, the total cumulative precipitation over the entire set, and divide it by the number of years to get the average, because that's going to be my threshold to compare, to look at droughts. Okay, so copy, paste. Okay, all we do here with this integrator is we just get the cumulative precip coming in, and then I go down into the advanced options of the integrator, and I check a box to calculate the average over the entire duration that the simulation runs. That will give us the average over the entire simulation. And that's the number that I want to use as my threshold to determine whether we have a drought or a wet year. So this is a really important output, and we need to expose this on the submodel. So I'll go back up a level and go into the interface of the submodel, and then on the output side, I will add the output of the annual average precip. And before I do that, I'm going to turn off Monte Carlo on the submodel, because that just makes this interface more complicated if I have Monte Carlo. So I changed the simulation of the submodel to deterministic. Okay, and then I add annual precip. And the option here that I want is I want the final value, because that's what's calculated at the end of the simulation. That's what I want, the last calculated. Click OK. And now we have our annual average precipitation. This is actually simulation average precipitation over the entire duration. All right, the next thing I want to do is calculate array totals. And what I mean by that is I want to have an array that represents all the years that we have on record. So in order to do that, I need to create a new array set. So array label set, actually. So I go up here to array labels. You can also get that from model, array labels, either way. I go to array labels, add a new set, and I want to use an indexed set and call this years. And just for convenience, now I could say, well, I've got a, what do I have here? 36-year record, so I could just put 36 right here and have 36 rows. That's one way to do it. Another way to do it is to simply make your start index be the start year, 1985. And then the end year, 2021. There they all are. So now I have all the years in an array. Now keep in mind, this index, this is how you access rows in this particular array set. So if I wanted to get the value of the first row of this array, I would index it with 1985. It's just a convenience because it refers to the year is all. Okay, so now that I've done that, I want to then take the annual cumulative precipitation for each year and assign it to each corresponding row for each of the years. It turns out that we already have an example on our website for doing this very kind of thing. So I'm just going to copy and paste that into the model. And I will provide links in our webinar archive on how to access these particular models. So this did come from our library, and I can point you to that later. But it looks like this. And what it does is, first what we do is we have this integrator that just reads the time series as it comes in, and then we reset it annually. But before we reset it, we populate the vector. And this is the vector over here called annual sums. And so we use a discrete change that says, okay, I'm going to build a vector on the fly. As we're running through the simulation, I'm going to build a vector. And we're going to do that with an if statement that says, vector if the current row in the array, if the row equals the year count, and the year count is, again, the 1985 through to 2021. When it equals the year count, then go ahead and add the cumulative rain. Okay, then what we end up with is an annual sum. And you can get average and standard deviation stuff too, but what we're really interested in right now is the annual sum. I want the annual sum for each year, and I want to put that into its respective row in the array. Okay, so now that we can get that information, we can then expose that on the interface of the submodel. That's the array of the annual values. So I go here to the interface, add, and I go into the container where I have the annual sums. Now it's going to give me the final value, last calculated. There we go. And this is going to be an array. Another thing we could do inside the submodels, we could just make sure that the array is the correct size based on the number of years we have on record. So I could paste something like this in the model in which we are looking at the duration of the submodel in number of years, and then just make sure that that is going to be, in our case, equal to the number of rows in the array. So this is just a check, just to say, hey, you're running, if I happen to run a submodel that it ran for more years than what I have as rows in my array, then we would end up with a problem. It would return an error. We wouldn't be able to run the simulation. So it'd be nice to know if we have that problem. Okay, so with that check in place, now we are ready to start working with that information. So the first thing I want to do is I want to grab the average over the duration. So this is the average precip, which we will then use as the threshold to determine if we have a drought or not. And then I want to take the annual precip array for all the years and also have that available. Okay, the next part is where we do a lot of the work. Okay, and this is the work that we need to do to determine whether or not we have a drought or not. And so to do that, I'm going to create a new container, and I'll call this drought events. And what we're doing here is we're just, as we run the simulation, I'm just going to compare the annual precip value to our threshold. And if the precip is less than the threshold, that's considered a dry year. If it's greater than the threshold, it's considered a wet year. On top of that, I want some other rules. So I'll go in here to the drought events, and then I'm just going to copy some text into here just to make sure we get the rules right. So what I want to do is I want to say if the annual precip is below a specified value, then we are considered to be in a drought. However, we also need the drought to be more than 1 year. If it's just a 1 year thing, it's just a blip, and we consider this not to be a drought. It needs to be at least 2 years long. And then there are some other rules that I want to add. For example, another rule might be something like, in order to end the drought, we need to have at least 2 wet years. So at least 2 wet years to end the drought. However, there's one exception to that. If it's a very wet year, that will also trigger the end of a drought. A very wet year will also trigger the end of a drought. Okay, so it's getting a little bit more complicated, but we need to formulate this ahead of time. And then once we know all of these things, then we can start to assemble the logic for this. And so in order, also what we want to do is we want to say, here we said droughts less than 2 years are ignored. So if the if the annual precip drops below the threshold, that's not enough to say, oh, a drought has started, right? We need the drought to drop below the threshold at least 2 years. So that means I need to know what are the 2 years of drought, not just the current year, right? And then to recover from a drought, I need to know 2 years at least, unless it's a very wet year. But besides that point, I need to know if next year and this year are both going to be wet, and if so, that will end the drought. Okay, so that means in addition to knowing the current year's situation, I need to know last year and I need to know the future, the next year. And so to do that, I'm going to use a few elements, which I will copy and paste into here to show you. Okay, so with these 3 elements, we have next year, current year, and last year. So current year is simple. The way that I get the current year precip, total precip, is simply by accessing the array that I was waiting for earlier, or sorry, that I was computing earlier, that I was telling you about. This is the entire array called annual precip, and so that contains all of the precip values from 1985 to 2021. And then I just simply give it the current year of the simulation, and it will then tell me the precip for the current year. And then to get the precip from last year, that's quite easy as well. I just use a previous value element. I could also use an information delay, perhaps, as long as it's delaying by the correct calendar year length of time. So either one of those, but that would give us last year's precip. So that's how I get current and last year. How do we get next year's precipitation? Well, the nice thing about having a submodel that generates this array of precipitation values ahead of time using a submodel is that now we have total access. We have access to the entire array immediately upon the start of the simulation, which is really nice. So because I have access to that entire array at the beginning of the simulation, I can access any value at any point in this array. So I'm going to do that simply by this end part of this equation. Don't get bogged down in the whole thing yet. Just look at this first part, right, or this part I've highlighted, which is looking at the array, and then it accesses the array with the year plus 1. So that's going to look at the next year, right? However, we need to be careful when we do this, because if we do year plus 1, when we get to the last row of the array, this would send us off the end of the array, which can't be done, right? That would give us an error when we run the model. So I need an if statement here that says, you know, if we are at the row, as long as we're looking at a row that's not the last row, right? So I use a less than here, and I say if our current year is less than the year at the end of the simulation. And by the way, this is a new function that's available in GoldSim 14 called getYear. All you have to do is type getYear parenthesis and then give it a date, and it will find the year of that date and return that. So I do start time plus sim duration. That's going to be the date at the end of the simulation. If the current year is less than that, go ahead and just say year plus 1 to get the next year. Otherwise, let's just say 0. We don't care when we're on the last row because we don't know what the next year is. That's the end of the simulation. We don't care. So this will provide us a safe way to access next year's precipitation value. Okay, so now that we have those, the next thing I want to do is bring in the threshold. And what I mean by the threshold is the average over the entire set. What's the average precipitation over the entire set? That's what we're using as our threshold point. Any individual year's precip that drops below this threshold is considered a dry year. So I need to know what that threshold is. That is simply the average over the entire data set. That's our threshold. So that's what we're going to be doing all of our comparisons on. All right, so the next thing I want to do is I'm going to use and these might be somewhat new to some of you. These are very powerful elements. I think they are very useful in displaying graphically conditional logic, the and, the or, the not, and now in GoldSim 14, we have the logic tree. I won't be using that because I don't have very many of these I'll be using. But if you're using a lot of these and, ors, nots, a logic tree might be a simpler way, more compact way to show your logic. But I'm only going to be using 3 of these. Okay, so I'll add an and with this and, this is going to require that we put in conditional statements in here, and all of those conditional statements must be true in order for the output of this element to be true. So I will call this dry, which is essentially going to tell us that when the output is true, when drought is on or enabled, when there's a drought, then this thing will indicate a true output. Okay, so I'm going to add 2 items here. The first one is that I want the current precip, the precip of the current year, to be less than the drought threshold. Okay, so to do that, I can just refer to any element that I want in here, which is the precip of the current year, but we need to do more than that, and I need to create a conditional statement. So I'll say less than drought threshold. So when the precip of the current year is less than the drought threshold, that means it's going to be a dry year. However, according to our rules, we need to add one more thing, and that is the precip of the next year also needs to be below. So I'll go here, precip of next year, less than drought threshold. Okay, so those 2 things need to be true. All right, so that's going to trigger a dry year. And instead of building the rest of these, I'm just going to copy and paste just for the interest of time. Okay, so we have here another and statement in which this is going to tell us if we have a wet current year and if last year is also wet. And I misnamed this. This should say current and last. Make sure that the current year is wet and last year is also wet, and that will trigger the end of a drought, a recovery from a drought. Oh, I forgot. There's one more data point that I want to put in here, or one more input, and that is a percent that defines a very wet situation. So I was mentioning here in the rules that a very wet year will help us end a drought. Will tell us, or will trigger the end of a drought. And how do we define a very wet year? Well, that's something that probably needs to be thought through, which I haven't really, but I did come up with a number just for the interest of presentation. And I just said, well, if the precip, annual precip is 25% greater than the threshold, that will trigger a very wet year, which would then allow us to then say, okay, that means we have currently a very wet year. So if I come over here, then we say our current year of precip is greater than the very wet threshold, which is indicated here. It's 1 plus the percent multiplied by the threshold. So that's 125 or 1.25 times the threshold. If our current year's precip is greater than 1.25 of the threshold, it's a very wet year. So then we can use an or element to say we either need a very wet current year or we need 2 consecutive wet years to end the drought. And that's an or statement, right? Either one of these 2 things will cause us to end the drought. And I called that element wet. So now we have dry, wet. These are the 2 elements that will now control the indicator of drought or not drought. And I will do that with a status element. I'm just going to copy and paste that as well. Okay, so here's the status element. Next to it is a not element, I'll describe in a second. But the status element, let's not worry about the not right now. The status element it has two triggers in it, the true trigger and the false trigger. The true trigger is set up to trigger to be true when the dry element is true. So when it's dry, that's going to trigger a drought. But on top of that, we also need to make sure that currently the drought is off. So we don't need to trigger a drought if it's already in drought. That doesn't make any sense. We only need to trigger a drought if it currently is not a drought, right? So I'm going to check the box to say currently the drought is not occurring, and all of a sudden we've triggered true here. That's going to trigger the start of a drought. Similarly, on the false trigger, we have to have a wet definition here in our wet output. That needs to be true. But then also we need to be in a current drought in order to switch it to not drought. And the nice thing about a status element is it's a state variable. It's a state element, and what that means is that it carries forward its previous value on each time step. That means you can refer to itself without having any kind of recursive loop or recursive error in your model. But what we can do is say, let's refer to itself. If we have a current drought going on right now, then we can trigger this status to be false by looking at this wet output. If this wet indicator is true and we are currently in a drought, then go ahead and trigger this to false. And false means we are not in a drought. True means we are in a drought. Okay, so that's how we switch between drought and not drought. And then I have a not element that I'm using that simply takes any kind of conditional output and makes it the opposite. So if drought is on, this will output off. And it's just a way to provide a name that makes sense in subsequent equations. Instead of saying, if I were to refer to drought on, and I wanted to say, well, when it's not on, I'd have to write the word not or put an exclamation point in front of drought on. So that's another way to do it. But I just like to have a separate element that makes it very clear, okay, drought is off here. And that's going to be used when we do our statistics. Okay, so now we have been able to characterize when the drought starts and when it ends. And so now we can run this model. We should be able to run this model, hopefully. Okay, we can. Now we can run the model and we can look at a comparison of the drought on status and the precip. But I'll just come in here and do that right here. So I'll look at the current year and I'll look at the drought on. I'll just create a time history. So we want the precip of the current year, and then I want to look at the drought on output. When we compare these two things and show a plot, then what you see here is that, oh, and then we also want to compare it to the average. So the average is actually the drought threshold. Okay, so here's the drought threshold. And one more thing is we're running this on a 1-day time step, which we really don't need because we're only evaluating things on years. So I will go back in here to the simulation settings of the main model and then change this to calendar years. Okay. Now when we run the model, okay, there we go. And I'm just going to add some points here. Okay, so this just makes it a little bit easier to see. So what we have now is a chart that shows the current precipitation along with an indicator of drought. And the blue line indicates drought when it is a value of 1 on the Y2 axis. And then it shows a value of 0 when it's false, indicating not drought. Okay, so the red line is our annual precipitation as compared to the drought threshold in green. And let's just walk through this logic. So at time 0, the value is above the green line, indicating we start out in a situation where we are not in a drought. So that's why we're 0. Then the value drops down below the threshold for at least 2 years. That indicates drought. So now we are in a drought. We go forward, we have one value above, but that's not enough to get us out of the drought. And then we have another low one, and then we have this really high precip year. And that was enough to pull us out of the drought, because if I compare the very wet threshold, and I'm going to make this also green, but with a different line style, then what you see here is if the precip is above this dashed line, just 1 year will trigger the end of a drought. So that's why the drought turns off. Following that, we have 2 consecutive years of dry, turns it on. And then over here, 2 consecutive years of wet, that turns it off. And so on as we walk through. So that's how we've implemented this logic. And now you can see we have a 5-year drought here, a 3-year drought here, a 9-year drought here, a 3-year drought here, something like that. I might have gotten those a little bit off, but that's what we've ended up with here. So we have 4 droughts in this particular simulation that I'm doing using those rules. Okay, so now I'm going to come up here, and now we want to characterize those droughts by quantifying the duration of each of those periods. How do we get the duration of the drought? So what I'm going to do is use a combination of discrete change elements and integrators. And in the interest of time, once again, I will do a copy and paste. Okay, and I'll just walk through the logic here. So I've created another container called Drought Stats, and when I go in here, then what you see is a couple of expression elements. One is the precip shortage, and what I mean by that is what is the difference between our drought threshold and our current year precipitation, just to see how far down or how far below our threshold we are to characterize the magnitude of the drought. If the dry year, if it's just slightly dry, right? If our annual precip is just slightly below the threshold, then it's less of a magnitude, right? It's a lesser of a drought than if, say, it's very far below the average. And so I want to define that by calculating the difference. And so if I open up this expression, then what you see here is I'm looking at the drought threshold and subtracting from that the current year precip. I don't want to see a negative number, so during a wet year, this would be negative, and I don't care about that. So I'm just using a max function here with a max of that versus 0 to just strip out anything that's negative, which I don't want to look at. Okay, the next one is the counter. I want to count how many droughts have occurred over the simulation. That's a good way to get the frequency of these droughts, but I also use it for other things. And a very easy way to count events in GoldSim is to use a triggered event and then look at the output of the triggered event called event count. This is a very simple way to count things or count events that have occurred. So I do that with a triggered event, and then if I look at the trigger, it says when the drought is true, when it becomes true, I should say, when it's on true, it triggers one time. That's the start of the drought. It counts each start of drought, essentially. Let's see, I put an interrupt in here. Okay, so it turns out that I want to put the information about each drought into an array of my droughts. So I have to build another array label set that is a placeholder for the information about each drought. So I created a new drought array label set, and I just gave it 10 rows arbitrarily, hoping that 10 is enough rows to quantify all of my droughts that I'm looking at. Well, I already know that I have only 4 droughts in this time series set, so 10 is enough. But you'll want to make sure that you put a number large enough to hold the information about all the droughts that have occurred. So I put an interrupt element in here just to make sure that this array is big enough to hold at least all of the droughts that I have. And so the way that you do that is in an interrupt element, I just say, make sure that your drought event count, or the number of droughts, make sure that it's not bigger than the number of rows in your array. If it is, then trigger this interrupt and tell the user, hey, you've got more droughts than you have rows in your array. That's going to be a problem, right? So that's why I put that in there. Okay, so now we are counting the number of droughts, and with that number, then if I go over here to add shortage, with that number, then I can use this number to assign quantified outputs that characterize each individual drought to a specific row of the array. That's why I'm using this drought counter. Okay, so with this discrete change, then we can use a vector constructor that says if the current row of this array, the array of droughts, if the current row is equal to the counter, the drought count. So let's just imagine for a second, we're looking at the first drought. If the row, and it's going to walk over this entire array, if we're looking at the first row, if that equals the first drought, then that's what we want. We want to put the precip shortage amount into that row. If we're on the second row, it will wait until drought counter is number 2, and then assign the shortage to the second row. And this is a really easy way to essentially construct an array of these specific outputs as it walks through time and stuff them into a new array, which is what I'm doing by adding this discrete change into this integrator. So it's a very easy way to essentially, as you walk through time, assign a value to subsequent rows in an array as you walk over it through time. So that's how we add the shortage, and this is how I'm going to get to the point of understanding the magnitude of the drought. The next one is the drought duration that I want to get. So to get the drought duration, then what I do is I'm essentially going to add a year. And it turns out that because my simulation is running on a 1-year time step, then I'm just going to add a 1 every time we find out that the row is equal to the drought counter. So for example, if we're on number 2 and we are on the second row, then it's going to add a 1. But on the next year, it might still be number 2. So then it will add another 1. And so as during the entire duration of the drought, it will continue to add 1 again and again and again during that drought. And so that's how I add the number of years that in which the drought is occurring. And so then I put that into a duration array, which at the end of the simulation, it should tell us how many years the drought has been occurring. Once I have the duration, then we can get the magnitude, because then I want to say, okay, I have a total, I've added up all of the total shortages of precipitation, and I want to divide that by the duration to get the average magnitude of the shortage or drought during the period of drought. And so that's why I divide by the duration. And that will give us a vector of average magnitudes of the drought. So essentially, I'm looking at these two outputs over here on the right, the duration array and the magnitude array. Okay, so now we have those two arrays, and now we are ready to look at the information. And what I'll do is I've already got those elements here. This is the same model that I was copying from. If I run this model, then we can look at a history. So here is our history we're just looking at, where we have the annual precipitation and then the drought indicator. And then we can look at the drought duration in a table using a final value chart. I can do this with a chart or a table. A table makes more sense in this case. But you can see that the duration for a year, for the first, not year, these numbers indicate the number, the drought counter. So on the first drought, it's a 5-year drought. On the second drought, it's a 4-year. On the third one, it's a 9-year drought. The last one is a 3-year drought. And then we can also look at the magnitudes of those. And we probably don't need so much precision there. That's a lot of precision. Okay, so the first drought is about 17 inches on average. The next one is about the same, so pretty significant. The 9-year drought is quite a bit less, so it's not a high magnitude. The magnitude is not as great, but it's a much longer drought, and so it's a good way to measure the different aspects of these droughts. Yeah, it was a long drought, but not as intense, you could say. And then finally, the very last one, the 3-year drought, which was averaging only 12 inches below the average. So this is a good way. Having the duration and the magnitude is a good way to measure these different droughts. And so with this information, now that we understand and have been able to characterize these droughts, this gives us the ability to model them going forward. So now we could build a model that will, on average, generate similar droughts as what we saw in the historic record, but they will be synthetic. They will be never before experienced situations going forward, which is a more powerful model than simply just assuming that the historic record is what we're going to see repeated again, right? So doing this kind of modeling allows us to build a more robust model to give us more coverage into the future, more possibilities, and but also realistic because they are based on the historic record. So that concludes the webinar. I hope it's useful for you, and I'm happy to take any questions. I'll wait around here for a bit to see if there's any questions from anyone. And if not, thank you very much for joining, and we hope to see you next year. Also, happy holidays, Merry Christmas, and Happy New Year.